Good morning, students. Yesterday we discussed various characterizations of continuity. All those characterizations can be summarized in the following theorem. So the theorem is, for the two topological spaces x tau and y tau dash, f is a function from topological space x into y, then we are to prove that the following conditions are equivalent conditions. First condition is function f is continuous. Second condition, inverse image of every open set in y is open in x. And third condition is inverse image of every closed set k in y is closed in x. And fourth condition, for every a subset of x, image of a closure under f is contained in the closure of image of a under f. And the last condition is, for every subset b of y, the closure of f inverse b is contained in f inverse of b closure. So these are the 5 conditions which you are to prove equivalent, and all these conditions we discussed in the previous theorems. So firstly you will do 1 implies 2, then 2 implies 3, then 3 implies 4, and then 4 implies 5, and then you will have to do 5 implies 1. So all these theorems we have discussed in the previous lecture. So you will do these theorems from those topics. Now next our topic is continuity of composite of two functions. So the theorem is, let us take 3 topological spaces. First topological space is x tau, second is y with topology tau dash, third is z with topology tau double dash, and we have functions f from x into y and g from y into z. Let us take a point x naught belonging to topological space x, and the function f is continuous at the point x naught, and the function g is continuous at f of x naught. Then we are to prove that the composite function, this function f is from x into y, the function g is from y into z, then the composite function, which is a function from x into z, this is a function GOF, composite of the functions g and f. We are to prove this function is continuous at the point x naught. This is the point x naught. Suppose this is the point f of x naught. Function f is continuous at x naught. Function g is continuous at f of x naught, and we are to prove that this function GOF, that is continuous at the point x naught. Now we use the definition of continuity in order to prove this. In order to prove that the function GOF is continuous at the point x naught, let us take a neighborhood of GOF of x naught. That neighborhood we have taken as W. Now this function g is continuous at f of x naught. So by definition of continuity, there exists a neighborhood h of f of x naught such that image of this neighborhood under G is contained in the given neighborhood. The given neighborhood is W. So we can say that image of H under G is contained in W. Now from here, because H is neighborhood of f of x naught and the function f is continuous at the point x naught, so again by continuity of the function f, there will exist a neighborhood V of x naught such that the image of this neighborhood under function f is contained in the given neighborhood H, where H is the neighborhood of f of x naught. Now we are to find the image of this neighborhood under the composite function GOF. So let us find the image of V under GOF. Now by definition of composition of two functions, this can be written as g of f of v. Now f of v is contained in h, so we can say that this is contained in g of h. Now g of h, that is contained in w. So we have proved that image of the neighborhood of x naught under the function g of f, that is contained in w, where w is the neighborhood of image of x naught under g of f. So this proves the definition of continuity at the point x naught. So this proves that composition of continuous functions f and g is again continuous at the point x naught. Now the next theorem is, let us take three topological spaces x tau, y tau dash and z tau double dash, and f is a function from x into y which is continuous, g is the function which is from y into z and is continuous function, and we are to prove that the function g of f from x into z, that is continuous. In the previous theorem, we proved the continuity of this function at a particular point x naught. Now we are proving the continuity of this function for the whole space x. Now to prove that the function g of f is continuous, we show that inverse image of every open set in z is open in x. So let us take an open set in z. Let us take that open subset of z is h. We are to prove that the inverse image of h under the function g of f, that is open in x. Now because the function g is a function from y into z and this function is continuous function, so by definition inverse image of every open set in z is open in y. H is open set in z, so its inverse image under g will be open in y. Now g inverse h is open in y and the function f from x into y is continuous. So inverse image of every open set in y, that will be open in x. So its inverse image under f, that will be open in x. So we can say that g of f inverse under h, g of f inverse h, that is open in x. This proves that inverse image of every open set in z is open in x, and this proves the continuity of the composition of the functions f and g. Now next characterization of continuity is given in the following lemma, and this lemma will be used in the next theorem. Let us take two topological spaces x tau and y tau dash, and f from x into y be a function. Beta dash, this is the base for the topology of y. Then we are to prove that the function f is continuous if and only if inverse image of every set belonging to beta dash, inverse image of every member belonging to beta dash belongs to tau. It means f inverse g belongs to tau for every g belonging to beta dash. It means inverse image of every member of base is open in x. So first of all, let us take the function f is continuous, and let us take a member g belonging to the base for the topology of y. Now because beta dash is base for the topology of y, so by definition of base, that is a sub collection of the topology tau dash. So beta dash is sub collection of tau dash. So every member which belongs to beta dash, that will belong to tau dash. So g belongs to tau dash. Now because the function f is continuous, so by definition of continuity, for every open set in y, its inverse image will be open in x. Now this is open set in y, so its inverse image will be open in X. So we can say that F inverse G belongs to tau, and this proves the first part of the theorem. Now let us do the converse part. Conversely, it is given that the inverse image of every member of base is open in X, and we are to prove that the function f is continuous. So in order to prove the function is continuous, we prove that inverse image of every open set in Y is open in X. So let us take an arbitrary open set in Y. It means G belongs to tau dash. Now because beta dash is base for the topology of Y, so by definition of base, every tau open set can be written as union of members of beta. Here the topology is tau dash, so we can say that every tau dash open set can be written as the union of members of beta. So we can take a sub collection beta of beta dash such that G can be written as the union of the members of this beta. Now let us find its inverse image. F inverse of G, substituting the value of G here, so this will become F inverse of union of A, where A belongs to beta. Now this can further be written as union of F inverse A, where A belongs to beta. Now F inverse A, we are given that for every A belonging to beta dash, its inverse image belongs to tau. So we can say these members belongs to tau, and because tau is a topology that is closed under arbitrary unions, it means arbitrary union of open sets is open. So we can say that union of F inverse A, where A belongs to beta, that belongs to tau, and from here we can say that F inverse G belongs to tau. This proves the continuity of the function f. Now in the next theorem we are to prove the same theorem for the subbase. So let us take two topological spaces x tau and y tau dash. These are two topological spaces, and f is a function from x into y, and let us take alpha dash be the subbase for the topology tau dash. Then we are to prove that the function f is continuous if and only if f inverse G belongs to tau for every G belonging to alpha dash. Here alpha dash is subbase. It means inverse image of every member of subbase is open in X. In the first part, let us take a member G belonging to alpha dash. This be an arbitrary member of subbase. Now by definition, subbase is a sub collection of topology. So we can say that alpha dash is a sub collection of tau dash. It means every member which belongs to subbase, that will be also in the topology tau dash. So we can say that G belongs to tau dash. Now because the function f is continuous, so by definition of continuity, inverse image of every member of tau dash, that will belong to tau. So we can say that f inverse G belongs to tau, and this proves the first part of the theorem. Now in the converse part, we are to prove that the function f is continuous, and we are given that the inverse image of every member of subbase that belongs to tau. So in order to prove this part, we will use the above lemma, in which we have proved that a function is continuous if inverse image of every member of base belongs to tau. So let us take beta base for the topology tau dash. Let us define beta. Now we already discussed that the collection of all the finite intersections of the members of alpha dash that forms a base for the topology. So let us define base by taking the finite intersections of members of subbase. Now alpha dash is subbase, so let us define beta as a collection of all those A which are subset of X, and they are the finite intersections of members of alpha dash. Now by definition, this beta is base for the topology tau dash. Now to prove that the function is continuous, let us take a member from this base. This is an arbitrary member, and we are to prove that its inverse image under F that belongs to topology tau. Now because G belongs to beta, and by definition the members of beta are the finite intersections of members of alpha dash. So by definition G can be written as intersection of AI, and these AIs, they belongs to subbase, and these intersections are finite intersections. Now let us find the inverse image of this G. Now F inverse G, substituting the value of G here, and this can further be written as intersection of F inverse of AI. Here I varies from 1 to n. Now because F inverse of AI, they belongs to tau, and tau is a topology that is closed under finite intersections. So we can say that intersection of F inverse AIs, they belongs to tau, and we have proved that F inverse G belongs to tau for every G belonging to the base of the topology tau dash, and this proves that the function F is continuous function. Now let us see some examples of continuous functions. So first example of continuous function, if we take a topological space X tau with a discrete topology. Discrete topology is the collection of all the subsets of X, and Y is any another topological space having the topology tau dash. Then the function from discrete topological space into Y, that is continuous function. So in order to prove this is continuous, let us take an open set in Y. So that open set we have taken as G. G is open in Y. Now by definition F inverse G, that will be a subset of X, and all the subsets of X, they belongs to the power set of X. It means F inverse G belongs to power set of X, and power set of X, that forms the discrete topology. So we can say that F inverse G belongs to tau. Thus we have proved that inverse image of every open set in Y is open in X, and this proves the continuity of the function F. Now another example of continuous functions is if we take any topological space X tau and Y is in discrete topological space with topology tau dash. Here tau dash is in discrete topology consisting of the members Y and phi. Then this function F from X into Y, that is continuous function. In order to prove it continuous, let us find the inverse image of every open set in Y, and we prove that that is open in X. Now because in this topology there are only two members, phi and Y. If we find their inverse image, F inverse of phi, and that is phi, and phi already belongs to the topology tau, and also F inverse of Y, that is the whole space X, and X belongs to the topology tau. So this proves that inverse image of every open set in Y is open in X, and this proves the continuity of the function F. And this completes the topic continuity of the functions in topological spaces.